Good afternoon. My name is George Paris. This is the third part of a series of videos I'm doing on thermodynamics. This particular part has to do with statistical thermodynamics, something I haven't taught much in terms of undergraduate students. I don't teach many graduate students, but I think you'll find this interesting. If you haven't seen the first two parts, you probably ought to go back and watch them. Part one has to do with heat and heat capacity, and then part two was sort of a classical development of uh, uh, entropy, enthalpy, and free energy. I took it that order because of if you go into the history of this, that's more the order they actually got sorted out, which might seem odd to some of you. Okay, so now we're going to deal with something called statistical thermodynamics. And this was brought about by a fellow by the name of Boltzmann. We're going to talk about him quite a bit. But let me first get a plug in here. Okay, here's the book. I've written, this has been published since 2019 or before. There's earlier editions. And you can buy it on Amazon.com. It looks like $6.38. The books standalone, the videos are standalone, but they are also directly interrelated. So if you want to use the book and the videos together, that'd be great. If you want to use the book, if you want to use the videos, whatever. Videos, of course, are free. We're here on Amazon. No, we're on, excuse me, YouTube. The books are on Amazon.com. And that's a paper, but you can actually get looks like the Kindle edition's only $2.75. So this is not going to break you up. I'm not making any money doing this. I'm doing this primarily because I think it's useful to students, and I think it's going to clear up a lot of confusion that students have. Okay, let's go to talk about Boltzmann. Parts 1 and 2 have summarized the history and status of conventional thermodynamics. These videos show thermodynamic necessity of considering entropy as well as enthalpy in evaluating the spontaneity of chemical reactions. But it may seem odd that while the free energy of a system is clearly a state function, that is, it's independent of the pathway you use to get there. Doesn't matter how you got there. Once you're there, you have a certain number of atoms and molecules. They have a certain amount of energy at a certain temperature and pressure, and that's it. And it doesn't matter how you got to that point. They're all going to be the same. Okay, so that's what a state function is. In any event, it may seem odd that since we're claiming it's a state function, if you go back through the Clausius approach, you find out that we're following a pathway. We're looking at solids, and we're looking at phase change, liquids, phase change, gases, phase change. How does that all work together? In addition, not only should the free energy of the system be a state function, but all the pieces that go into it, the enthalpy, the entropy, that would be T times S, they all should be state functions. And how do we get there? Now, Ludwig Boltzmann, he's a he's a mathematician and a physicist, and he's thinking, hey, it's supposed to be a state function. I should not have to have a mapped out process, a pathway, in order to get this number. How do I do that? Okay, that was sort of his goal from the start. He advanced towards his goal in various steps. Boltzmann was a theoretical physicist, mathematician. I think he also was I think he was Lise Meitner's mentor. I'm not sure. Check that one. He looked into the molecules, and he realized that the history of the transitions of a system from absolute zero, T equals absolute zero, to some arbitrary standard state, T is equal to some standard temperature, T sub zero, is inscribed in the energy levels. Recall that the ability of a molecule to store energy is tied to the energy levels that are available to the molecule. Thus, Boltzmann reasoned that if he knew the energy levels available to the molecule, he did not need to know the pathway by which the molecule reached its current state. On the right here, I have an example. Actually, this, I think, appeared in part 2 or part 1 of this series of videos. On the right, I have 6 vibrations, and they're at a scale of x equal 1. To get everything on the same scale, more or less, to make it visible, I took the translations and the rotations, which have a much smaller energy level separations, and put them there. There's 3 of those. So this happens to be, I think it's formaldehyde, was an example I used back, I think, in the first part. So anyway, this is just to remind you that there are a bunch of degrees of freedom. There's 6 vibrations, 3 rotations, and 3 translations, and they all have energy level separations that are characteristics of those degrees of freedom. Now, first thing that Boltzmann went into says, okay, can I show that heat flows from hot to cold? And this, I mean, it's intuitive that it does that, and obviously we observe it happening all the time. He tried to come up with a variety of explanations, and people were arguing against this, and he never was able to completely convince people, or even himself. He sort of dealt with it, you know, when people raised an objection, he would try to whack-a-mole that one down, but eventually he realized that in the end he conceded that his several lines of argument never completely proved his point, and that ultimately it was a matter of intuition that the universe would proceed to its most probable state even if the system under observation went to a less probable state. Okay, so the whole universe has entropy going to its most probable state, even if a system is going to a less probable state. So that's worth recalling. I highlighted that. Give you a second to think about that. Okay, now along the way, in a previous video here, we have already discussed the origin of Maxwell-Boltzmann distribution function. That's the yellow highlighted area to the left. I'm not going to go back into that. It's in the first 2 videos. It was first proposed by Maxwell in about 1860, and Boltzmann adapted it between 1872 and 1877. Obviously, the velocities of gas molecules are tied to Gaussian distributions. Their kinetic energies must also be tied to Gaussian distributions. And by application of equipartition principle, the energies of all degrees of freedom of the molecules must be described by Gaussian distribution. Since the events tractable by the Gaussian distributions are discrete, it is not surprising that Boltzmann began thinking along the lines of discrete energy levels associated with degrees of freedom of molecules. This was by 1877. Now, it turns out one of the factors that was hotly discussed at this time frame was the black body radiation. If you had something called the Rayleigh-Jeans model, that's the dotted line on the left here, it's directly above my head up there someplace. If you were, you have what people call the ultraviolet catastrophe. Basically the model broke down at short wavelengths, and so various people, in particular Max Planck, were trying to come up with a model that would allow the model had to represent what was actually observed in nature, and obviously Rayleigh and Jeans were not doing that. So here's Max Planck, and in the 1890s, Planck was a very classical and well-known and well-respected physicist. In the 1890s, he was unable to explain the spectrum of black body radiation with classical physics. He tried a variety of approaches, just didn't work, and he was not happy with the result of that. But reluctantly, he picked up Boltzmann's idea of discrete energy levels, and very soon he found he could create a model in which the theory based on discrete energy levels would allow him to come up with a model in which the theory matched the experimental or the observations. Now, Planck still didn't like this. He was always very skeptical of this discrete energy level concept and whatnot. But I, he ended up using it. He proposed it, and then he was sort of saved by Albert Einstein. There'd been something called the photoelectric effect. I guess Hertz had come up with that. And Einstein in 1906 proposed a solution to that using the same idea that Planck had just published. This had a big impact on Einstein because Planck said, "Oh my God, I've been saved." And he went over there and sort of snatched Einstein out of obscurity and helped make Einstein the well-known scientist that we know. So there's interesting history here. I've talked about this in a few other places, but keep this in mind as we go forward. Now, we need to talk. When Boltzmann went into statistical thermodynamics, he introduced some new terminology, or at least it came along with the explanation of what he's doing. And so we need to sort of keep that organized in our minds as to what we're talking about here. He introduced, or at least the statistical approach to thermodynamics introduces two concepts that we don't want to get lost. One is microstates, and that is the state of all the energy levels of energy in an individual atom or molecule, whatever the molecular entity is. Now, if you have a cluster of molecules, the microstates of all of those makes up a combined microstate, and I'll use the terminology microstate to talk about an individual atom or a collection of atoms. And these microstates change. Both, if you think about it, you got atoms colliding, molecules colliding, and energy that was in rotations, vibrations, translations gets turned into something else. In other words, you may have a low translational degree of freedom energy, and it gets hit by something that had a high vibrational energy, and the vibrational energy gets turned into translational energy, things like that. It just, these things are constantly exchanging energy, both in terms of collisions and also by exchanging photons, interestingly enough. And so the net of all this is constantly changing. Not the net, but the individuals are always changing. Both the microstates of an individual molecule is changing, and within that whole collection of molecules we call the system, there's the microstates are constantly interchanging energy. But the important thing here is that the observable energy of the system, the macrostate, in which it has, in addition to the energy, we're talking about the physical state, temperature, all that kind of stuff, all the things we can measure about it, they all are constant because the energy in the system is being constant. And also like pressure, temperature, all those, the outside parameters are staying constant. So the microstate patterns change instantaneously between the different atoms that make up the system. So if we look at that, let's take a very simple case. Let's say we got 10 carbon dioxide molecules. We'll label them A through J. And we got them in the gas phase at 298 degrees Kelvin. Together, each molecule is going to have 3 atoms times 3 and 3 is 9 degrees of freedom. And let's just take 2 of those degrees of freedom. One would be, say, the symmetric stretch, and one would be a translational direction. I'll look at those here. And what I've done here is I've just created, for those 2 degrees of freedom, I have defined a microstate. I just arbitrarily pull this out to show you what I'm talking about. In the case, if you look at the symmetric stretch, that would be the column on the left. I'm taking 2 molecules, E and H, and they're in their second energy level, and everybody else, A, B, C, D, F, G, and I, and I and J are all in the ground state. On the other hand, as we talked about back in the first video, the translational states are going to be much closer together, and so we've got a much bigger spread here. I've got, just arbitrarily put the different atoms in different energy levels. So this is the translation and the X-direction microstate. Now, there's no correlation between this. You can have a very high vibrational energy level, a very low translational, or vice versa. And so there's no correlation between these things that is required by statistics, but it might, for example, we talked about coupling of rotations and vibrations. So we do have that type of correlation, but we don't have we don't have a statistically driven correlation. All right. So the microstates are the patterns. I'm going to talk about microstates as of a collection of atoms or molecules, not as individual atoms or molecules. So the microstates are the patterns of molecular population within a degree of freedom. So that's the connection between degree of freedom and microstates. So you have a degree of freedom. Within that degree of freedom, you will have a collection of microstates for the system. All right, the thing that makes us consistent is that because the number of microstates is going to be limited by the fact that the total energy of the system must always be accounted for. I will show you that in detail in a second. This is just a little sketch here. You got a bunch of different degrees of freedom, things happen. The energy of the system stayed the same through the whole process, although the movements of the parts, that is to say the individual atoms within the molecules and the molecules themselves, changed. You turned vibrational energy into translational energy, okay? So the only observable total energy of the system, that is to say the macrostate, is a constant, because we're looking at a state function. We're not looking at individual pieces, which are the microstates are the individual pieces. The macrostate is what you can actually observe. Now, in Boltzmann's 1887 paper, which has a roughly translated title, concerning the relationship between the second main theorem of thermodynamics and the theory of probability, he introduced the idea of an observable macrostate for the system, PV NT of a gas, for example, was determined by the summation of all existing microstates. In other words, the position and momentum of every atom folds into this whole thing to make up the macrostate. All right. To enumerate the microstates, he assumed that the energy of the molecules, monatomic gases with kinetic energy, for example, was divided into discrete packages, energy levels, and that the system, this is, Planck picked up on this, and was divided to discrete packages, energy levels, and the system was described by molecules distributed statistically among the energy levels for each degree of freedom. The entropy of the system then was related to the probability of the sum of the microstates, and this system would tend to move to the most probable overall collection of microstates. Okay. An important point is the observable macrostate of the system, whatever that parameters you want to use to define it, was determined by the summation of all existing microstates. That is to say, the position and momentum of all the molecules and atoms in the system. Now, we have to sort of derive a relationship here. And I'm assuming that this is closely related to what Boltzmann actually did. This is not original with me. I think I've got this from a paper that I'll talk about in a moment. The mathematical expressions, for example, assume we have n identical molecules in a volume, and each molecule, has a position A in the volume, and the degrees of freedom x. We have x degrees of freedom. All right, the total number of degrees of freedom will thus be A times x to the power n. Okay, so the total degree of freedom in this first equation here, parenthesis ax raised to n. If we define a state function s as the product of a scaling factor, this is a tool we're going to use to introduce to do the mathematics here, k, multiplied by the natural log of the number of degrees of freedom we have, the next equation, s is equal to k natural log parenthesis ax raised to the n. You do a little math here, and that's s is equal to k n times the natural log of ax. Okay, this is simple enough. How do we relate it to the macroscopic thermodynamic functions, free energy, enthalpy, entropy? All right, consider what happens if the volume occupied by the gas is arbitrary and instantaneously doubled. All right, we're not taking energy out of the system in order to do that. We're just okay. You've got twice as much volume to move around in. Okay, we can do that. Mind that thought process without putting energy into the system. Okay, so the number of positions occupied by the molecules doubles. Instead of having the number of A positions, now we've got 2A positions. All right, so the final state function is going to be S sub F is equal to K in natural log of 2AX. Now, if we do the math, the typical math, we subtract take the final, subtract the initial conditions. We do that arithmetic down here in the next line. So that delta S is equal to Kn. And if you go through here, this is just logarithmic arithmetic. And you end up with Kn natural log of 2. Now, how does this compare to the macroscopic state functions? Well, if we go back and we want to look at energy, or change in energy, that would be change in heat, Q, we can integrate the PV term, pressure's constant, we're integrating from V is equal to V to 2V, and we substitute for P, nRT over V. And we end up with this equation at the top. And we're going to make the assumption that n, the little n, is going to be the number of moles, really. It's going to be the capital N divided by 6.02 times 10 to the 23rd. And if now we've introduced little n. But we still have, look at the equation, you still have the capital N there. Thus, if we define R, K, that would be that K, that constant we introduced earlier. If we defined it as R divided by 6.82 times 10 to the 23, we can now write that the change in energy, delta Q, is equal to KT natural log of 2. In other words, the natural log part is what's changing here, and it has to do with how many new energy levels we've introduced. That is how many more statistical positions we have. Or in general, in general, instead of looking at just doubling, we'll just use the term omega here, which is just we change the number of sites, number of options, and so it's a natural log of these numbers of options. But if you rearrange this equation, divide this equation through by t, you know that delta S is equal to delta Q over T, and that would be K times the natural log of this omega function, okay, for statistical purposes, where omega is the number of microstates at the standard temperature T sub 0. Okay, so that's the key takeaway from this page. Okay, now let's try to look at this a little bit harder and come up with an example that we can get our hands around a bit better. Okay, microstates make up the observable macrostate. That's what we have learned from Boltzmann's hypotheses. And in November 1900, Planck used Boltzmann's idea of a discrete energy levels to correctly predict the spectrum of black body radiation. And we're going to use we're going to use Planck's terminology with Boltzmann's idea here, where S is the KB, that's the Boltzmann constant, times the natural log of W. This function W is the key part of the statistics. W is the thermodynamic probability of the macro state. Following Boltzmann, W must be defined from the microstates. To put this in some context that we can easily comprehend, we're going to take a simplistic system, 1 degree of freedom and only a few molecules. Okay, if we start, it multiplies very quickly. So we're going to take 1 degree of freedom, and there's going to be only a relatively few molecules, so we can actually do some arithmetic here. W can be calculated for each microstate as follows. W is going to be the factorial of the total number of particles divided by the product over a series of I particles, in which we've got every case that the particles have, the I cases, is going to be factorialized by how many atoms are in that case. In other words, in a particular energy level I, you're going to have a certain number of molecules in that, and we will factorialize that number of molecules. And we're going to do the math here in a second, and you'll see it works out real well. Okay, so here we go to the next page, I hope. Oh. Anyway, remember this, and remember this. All right, two factors to take away here. This is going to show up on the next slide. Here we go. Okay, in this case, we're going to take a system of 7 particles X. Okay, and they're represented here on this table by the letter X. And we're going to arbitrarily decide that this system, the state function of this system, is going to be 13 units of energy. These are just arbitrary units. The energy levels on the left, energy level 0, 1, 2, 3, 4, and we're going to arrange our microstates such that in every case they have to have 13 units of energy, because that's the constraint we're putting on the system. The macrostate has 13 units of energy. All the microstates must be constrained to 13 units of energy. You can't have less, you can't have more. You can't gain energy, you can't lose energy. All right. Now, if you do that, and I picked out just 3 random examples here, microstate 1, microstate 2, and microstate 3, and I just arbitrarily put some the molecules in different energy levels to come up with a total of energy of 13. If you look across that horizontal line where it says total energy, you'll see that in every case we add up to 13 units of energy. And I've got different distributions of the particles among different energy levels. Now, down below, I have calculated both W, the factorials that we had talked about, and I have then plugged them in and got the log of the factorials of that function W. And that natural log of W is essentially S divided by KB. It's just a arrangement that allows us to focus on this natural log of W. W is going to be related to the statistical probability of S divided by KB. All right. So, in the first case, microstate 1, I'll spend a little time here going through the arithmetic so you sort of see it work. I've got 1 atom, 1 particle, 1 molecule in energy level 4. 4 times 1 is 4. That's how much energy that accounts for. Then I've got 3 in energy level 3. 3 times 3 is 9. So I've got 4 and 9. And then I've put all my other molecules, 3 of them, in energy level 0, which gives me 0 energy because there's no energy stored in that because they're all in the ground state. And so the energy in the system is 4 plus 9 is 13 units. And if I go in there, the total number of atoms or particles or molecules is 7. So 7 factorial, which is 5,040 if I did my math right, divided by the factorial for the first, the highest energy level, 4, there's 1. So 1 factorial times, there's 3 in the energy level 3, so it's 3 factorial. And in energy level 0, there's 3, so that's 3 factorial again. And that's those product of those factorials is 36. And if you took 5,040 divided by 36 and then took the natural log of that, you'd have 4.94. Okay, so microstate 2, similar mathematical operations. You have that 5,040 divided, it turns out to be 24. And now you've got a W term, or a natural log of the W term, which turns out to be 5.35. Now, the bigger that number is, the more probable the system is. And if I go all the way over here to number 3, I have natural log of 540. But now, if you look at it, because I have all these ones and twosies, I've got the factorial numbers go way down. And so now I'm only dividing it by 4. 2 factorial is 2 times 1 times 2 times 1, and everything else is 1. So you've got 4 divided into 540 natural log, and that gives you 7.13, and that turns out to be the maximum distribution you can have. So 7.13 is the most probable state. But that is not a unique microstate. It turns out, let me go to the next slide. All right. Anyway, I've got one more slide here. Notice that the number of possible microstates is limited by the constraint on each microstate. Okay, that's why we don't have thousands of microstates, because we have constrained everything. In this case, in this example, have a total of 13 units of energy. It can't change, can't go up, can't go down, because that is our state. That is, we can't create energy or destroy energy along the way. Now, in the table below, we will see what happens in this. Okay, here I went through and I figured out what the most probable microstates were. It turns out there's 5 of them, A, B, C, D, and E, and each of those, they all have 13 units of energy. And if you do the calculation of W, in every case, you end up with a factor of 7.13. That's the natural log of W. And they're all equally weighted. So those are my collections of my most probable microstates. If I add that up, if I go from left to right along each of those lines, for example, energy level 7, there's nothing there. Energy level 6, there's 1 case there. Energy level 5, you've got 2. Energy level 4, you've got 3, and go on down. And you notice that you get this sort of a pyramid look. Now, what we've left out of this, of course, these are just the most probable states. It's only 5 most probable states. But we left out the ones that are less probable, which typically have higher or lower numbers of atoms. So if you add in all the possible microstates, you would tend to put more at the top and more at the bottom, and it would sort of give you if you added a few on the bottom and added a few on the top, it would cause this to curve a bit more and go up higher. And here's what it would look like. Okay, this is just a approximation of the non-discrete numbers that you would have if you went through here, or if you had many. If you had a mole of X's, obviously you would have a lot more, a smoother curve. and you'd have to account for these less probable microstates, and so you'd end up with it go more up, and it would also go more out at the bottom. It would not change that much in the middle, okay? And so you would have this curve, which of course goes back to your distribution, your Boltzmann, Maxwell-Boltzmann distribution function, Ni over N0. And so all of this ties back together, which is kind of cool. Now, this work, by the way, I don't know, I think I cited on one of the other slides. There was a paper published in JChem Ed, I forgot the gentleman's name who published it, but I think it was called the shelf theory or shelf demonstration of statistical thermodynamics. And this is basically what he did, but he actually had shelves and he moved balls around on them to represent the microstates. I'm just doing this here with X's. And so this is, how we tie all this together. Now, one important thing we have to do here, okay, how do we reconcile Boltzmann's approach and Clausius's approach? You will recall that Clausius implied a step-by-step integration of the delta Q over T or Q over T function, in which you typically would start with a solid, you'd come to, it has a certain heat capacity, you go up a certain temperature, then there's a phase change, you have latent heat involved, then you have a liquid phase, that has a heat capacity, then you go to a gas phase, it has a separate heat capacity, and all this at latent entropy. This defines if you were doing this from experimental data, that's basically what you do. You do this integration piece by piece. But that's a single pathway. And we're saying over and over again that a state function doesn't matter how you got there. Why does that work? How does that work? Okay. So how do we get Boltzmann on the left and Planck on the right, or excuse me, Clausius on the right, to see eye to eye? Here's the problem. In all of your chemistry books today, you're going to find this equation. You're going to see that delta S of a phase change is going to be delta H of a phase change divided by the temperature of the phase change. And we focus on that, and because it's very hard to get a delta S for a reaction typically. But this is a case where we can measure the heat of the phase change, heat of vaporization, heat of fusion, etc., and divide it by those temperatures of the phase change, and we immediately have the delta S. So that gets everybody very excited about how to get the number delta S, which we have managed to make very mysterious. I mean, the way we do thermodynamics, if you haven't looked at the first two parts of this, go back. We've managed to make thermodynamics very mysterious, especially the entropy term. But here has a very simple way to calculate that. And so we've gotten very excited about it. We focus on this equation, and it's exactly backwards, okay? This interpretation is wrong. It's not looking at this from a thermodynamic standpoint. Here's what you should be looking at. It is instructive to look at a plot of the vapor pressure as a function of temperature. You will find that in spite of the dramatic onset of boiling, the vapor pressure curve is completely monotonic. It just smoothly changes. As you heat it up, the vapor pressure just goes up. There's nothing at 100 degrees Celsius, there's no dip or change in this line at all. Okay. Now we, as we observe a liquid, we start heating it up. It's a liquid, everything's going smoothly, and then suddenly at 100 degrees Celsius, water will start to boil. Suddenly we got these bubbles coming, and we focus on that and we say, oh my God, something exciting is happening, and we apparently seem to think that has something to do with thermodynamics. It actually has nothing to do with thermodynamics, nothing directly, nothing important to do with thermodynamics. What is happening, obviously, is when we hit that boiling point, the vapor pressure of the water has exceeded the pressure of the atmosphere above it, plus whatever hydrostatic number we might have in there, because there's some water pressure pushing down as well with heating at the bottom. But in any event, you've got this, this dramatic event, this boiling occurs, but it is not anything indicative of thermodynamics. It's just an artifact of the way you did the experiment. Same thing with the melting point. Okay, it's nothing. There's nothing thermodynamically exciting about that, except we can explain that. Let's go back. If we look at the delta G of the phase change, we could go through this derivation. And the way we should look at this is we should rearrange that equation, that the temperature of the phase change is the dependent variable. The independent variables are the phase change enthalpy and the phase change entropy. The temperature of the phase change is the dependent part of this. Okay? Basically, the phase change is not driving the thermodynamics. The thermodynamics are driving the phase change. If we look at a phase diagram, or a typical plot here, you will notice that the vertical red arrows I've drawn in there, that's the energy involved in the phase change. That's the delta H of the phase change. And that number is only available one place. You've got a liquid that has a certain heat capacity that changes with temperature. And you have a solid that has a heat capacity that changes with temperature. And there's only one place where those two lines are separated by that amount of energy. And that amount of energy happens to be the delta H of the phase change. So we haven't put any constraints on this. It just turns out that the delta H of the phase change, represented by the vertical red arrows, the dotted lines, whatnot, there's only one place that they match. The change in the heat capacity. The heat capacities converge, and at that place where the delta H is the same as the T delta S, bang, you can have a change of phase. Otherwise, the system has to be in equilibrium throughout the process. And so at that phase change, you will change from being a solid to being a liquid, or from a liquid to a solid, depending which way you're going. Okay. And so it's a simple matter that in order to get this phase change, you have to account for the change in the heat capacities of these two systems. And so the observed phase change, that is to say delta H of fusion, delta H of vaporization, the only place you can do that is at one spot where the delta H for this process is going to be accounted for by the T delta S of the delta C sub V of the change in the phases. So the only place where you get the phase change is going to be at that temperature. The temperature itself is not something that has thermodynamic significance. It's the delta H and the delta S that have, or the change in heat capacity is the thing that matters. Basically, Clausius' approach works because a phase change exactly compensates for the difference in Boltzmann's macrostates. And Boltzmann's approach works because the current macrostate statistically integrates all the energy of all previous states, whatever they may have been. So that's it. I mean, it's not that big a deal. This is actually a relatively short video. I'm not sure, probably around about 20, no, it looks like about 45 minutes instead of an hour. But it's really not that complicated. That paper that I mentioned earlier, the one in JChem Ed, if you haven't read that, you really ought to. It's a nice little paper, gives a demonstration. Hopefully my graphics do accomplish sort of the same thing. But statistical thermodynamics does not have, if you try to do lots of degrees of freedom and lots of molecules, obviously it gets out of control very quickly. But if you focus on a simple system, it makes pretty much total sense. And you're basically just trying to maximize the probability of the various states. And so that's where you come up with the driving force for the reactions, essentially.